Good morning, everyone. This is the next group of refractory materials, the basic group. So we did some case studies on alumina silica type refractories. And each type of refractory, the strategy may vary somewhat because the chemistries are different. There may or may not be phase transformations. The thermal expansion coefficients are different. So each type of refractory will have some variation on how to improve the thermal shock resistance. So I have four different case studies here on basic refractories. The first one is thermal shock damage resistance of refractories, a 1974 paper, one of the older papers. So they correlated strength, Young's elastic modulus, fracture surface energy, the work of fracture surface energy to thermal shock damage. And they did an air quenching. And they looked at MgO refractories, MgO chrome refractories, and they also included some alumina silica refractories. So they looked at the relationship between what they call the modified R4 prime and the thermal shock damage. And these are fairly coarse grain refractories. So they just divided R4 prime by the volume under stress. So there's just another term here in the denominator, a volume term. Not sure why that was necessary because all the samples are the same volume. So the materials were some high MgO refractories with 95% MgO, some mag chrome refractories between 60 and 80% MgO, and some alumina silica refractories between 60 and 70% alumina. So they measured mechanical properties at room temperature, Young's elastic modulus. They use a sonic, the dynamic technique, a sonic velocity technique. The fracture surface energy was measured on a notched bend bar. The bend bars had 1-inch cross sections, were 6 inches long, and they measured also a 3-point bending strength. And they measured thermal shock on the half bars from the fracture surface energy test. So they were 2.5 inches long, 1 inch in cross section, and they quenched from 2200 degrees after room temperature, 15 cycles, and used a 3-point bend strength on a 2-inch span to measure the damage. Technically, on a 1-inch thick sample, it's usually 5 times the thickness is the lower span. So technically, it's not a valid MOR test. It should have been a 5-inch span, but that's what they used. So the MOR versus number of cycles, and I just said 15 cycles on a couple of them. They actually did 30 cycles. So this is the strength loss for MgO, the alumina silica materials, and then the mag chrome materials. And usually about 5 cycles in, you really reached your maximum damage. So the strength tends to level off. So you're thermally shocking under the same thermal stress conditions. The cracks grow in from the surface a certain distance and for that stress field. So that's why they level off. You'd have to increase the thermal stress to have more damage. So usually after 5 cycles, these level off. And they plotted strength loss, and this is R4 prime. And the MgO and the alumina silica fell on this line. And then the mag chrome fell on this line. So the higher the R4 prime value, increasing from left to right, the lower the strength loss. This had a separate curve, and the mag chrome materials go through oxidation reduction reactions with the Cr ion. So that causes volume expansions and microcracking. So that's probably why this has a higher strength loss than these other two groups of materials because of the oxidation reduction mechanisms. And they actually measured linear change versus the number of thermal cycles. So this is 5 cycles. And this is for the mag chrome material. So they actually saw linear change, 0.8%, due to this oxidation reduction mechanism where the Cr ion changes oxidation state. And that just degrades the strength because of this damage and the linear increase in the dimensions of the sample. So that is probably part of the explanation why this has worse performance. So this is strength loss for MgO and the alumina silica materials. And this is basically the inverse of R4 prime is the stored elastic strain energy. So the higher the stored elastic strain energy in the material, the greater driving force for fracture, the higher the strength loss. And this is again for the MgO and the alumina silica materials, strength loss now versus our R4 prime. And again, the higher the R4 prime value, the lower the strength loss. So there is a pretty good correlation with R4 prime and thermal shock damage. And this is plotting R4 prime versus strength. And this is for all the materials. So the magchrome, the magnesite, and the alumina silica. So they fall in this band here. This is the MOR before thermal shock. There are some outliers here. And when they looked at the microstructure, these had a very fine pore size distribution, and they had high work of fracture. So because of their microstructure, they were outliers. So what they concluded from this work, high fracture surface energy and stress relieving ability accompanying the liquid formation does not exist at low temperatures. So these are brittle type materials with perhaps a silicate glassy phase. So they're saying thermal shock damage is usually a maximum at the lower temperatures where the material is brittle. And in general, the thermal shock damage is a maximum just below the temperature of first liquid formation where the refractory is still brittle. And then the fracture surface energy increases substantially above this temperature where liquid formation starts. And that further retards crack propagation because of stress relief. So in this study, all the properties used to calculate R4 prime were measured at room temperature. And they concluded that R4 prime calculated in this way can be used to evaluate the thermal shock behavior when the material is thermally cycled in the, let's say, the brittle temperature range. So as long as the material is still brittle, below where silicate phase is softened, if you measure your properties like work of fracture and strength at room temperature, that seems like a valid R4 prime in that temperature range. So the next paper is by the same two authors a few years later in 1976. So they decided to look at fracture surface energies at high temperatures. So now they measured the work of fracture, gamma WF, from room temperature to 2,700 degrees F for the same group of refractories, the magnesite group, the magnesite chrome, and the alumina silica. So they're looking at the effect of temperature on the fracture surface energies. Same materials, 95% MgO refractories, mag chrome with 60 to 80% MgO, and alumina silica with 60 to 70% alumina. So the measured properties from room temperature all the way up to 2,700 degrees F. Fracture surface energies were measured on a notch bend bar. And it was 6 by 1 inches. So a 1 inch cross section, 6 inches long. And the strength was a 3-point bend strength. So this is the furnace arrangement they used. There's a mechanical test machine. This is the upper knife edge shown here, attached to a mechanical test machine, so they can use a constant strain rate to load the samples. So this whole arrangement is a furnace. The circles are the heating elements. The 1 inch cross section of the test bars are shown here. So the test bars are lined up on the floor of the furnace. And then there's a bar here, a push bar, that pushes the bars across to the lower knife edge. Both lower knife edges, the upper knife edge comes in, breaks the sample falls out, and then they push another sample onto the lower knife edges. So this is the arrangement they used. And for reference here, I've listed the work of fracture surface energy. The mag chrome brick, they had A through I compositions. The 95% magnesite brick, J through N compositions, and the alumina silica brick, O through T compositions. So room temperature, 1500 F, 1800 F, 2100 F, 2400 F, and 2700 F. And the units they use are inch-pounds per square inch. So in general, work of fracture tends to go up with increasing temperature and then fall off at some point. So I will show some graphs of some typical results in a few minutes, but this is basically a reference table of all the work of fracture results. They also measured the strength, and this is in PSI. Same refractories, the mag chrome A through I, the high MgO material J through N, and the alumina silica brick O through T. Same temperatures, room temperature, 1500, 1800, 2100, 2400, and 2700 degrees F. And you can see the strength values. Some of these, especially the alumina silicas, really fall off at higher temperatures. Some maintain their strength. But again, this is a reference table if you want to look at all the different results for the different compositions. So some of the results here, this is a results for 2 mag chrome materials that are direct bonded. So these have direct crystal contact. So the silicate phases are isolated. So they usually have higher strength at higher temperatures. So modular rupture versus temperature, and then the fracture surface energy versus temperature. So bricks B and F, F is stronger than B, and they both start to decline in strength above 2200 degrees F. And then they both increase in the work of fracture. This one, brick B, has a greater amount of direct bonding after the liquid forms. So it continues to rise in work of fracture, whereas the other brick F, falls off because it has a greater amount of liquid. So the degree of direct bonding, the amount of liquid that forms, it's a silicate liquid. These mag chrome bricks tend to have a a great deal of impurities in them. So their strength, and in this case, the work of fracture fell off where the silicates became less viscous. And if there's more direct bonding, this one maintained a pretty good work of fracture. This is brick N and J for the magnesite materials. There's a ratio of lime to silica that really determines the types of second phases that are present, the minor phases. And high lime to silica ratio has high melting phases. Low lime to silica ratios have low melting phases. So in this case, the high lime to silica MgO material has a much better strength as a function of temperature. Again, this is MOR versus temperature and fracture surface energy versus temperature. This one has low melting silicates, usually monticelite, muronite. So this really falls off. So the material with the high lime to silica ratio, the work of fracture actually increases because the silicate glass is viscous, it's isolated, and then that's a result of the high lime to silica ratio. Then the low lime to silica ratio, the material, the silicate glass is more fluid, it penetrates the grain boundaries, and the work of fracture falls off. So you can see from these examples, and this is the alumina silica, that the work of fracture is not constant as a function of temperature. So the same types of plots for the alumina silica material, MOR versus temperature, and work of fracture versus temperature. This brick is a super duty brick, and then the other one is basically a mullite material. So mullite material is a little bit stronger, but they both fall off about 2600 degrees F in strength. And because of the viscous silicate glass, the strength falls off and also does the work of fracture. They have maximum values where the work of fracture actually, because of the viscous silicate phase, dissipates energy and blunts the crack tips and really increases the work of fracture. So again, for any of these groups of materials, the work of fracture is not constant. So which one do you use? If you're thermally shocking at a temperature where you have a viscous silicate glass, do you use this work of fracture, or do you use the room temperature type values, much lower values? So they concluded from this work, in general, the thermal shock, I guess I pretty much went over this, but I'll do it again. The thermal shock damage is a maximum just below the temperature where the first liquid forms. So the refractory material is still brittle. And then fracture surface energy tends to increase above the temperature where the liquid forms, because the liquid retards crack propagation due to stress relief. It becomes plastic, it can blunt the crack tips, and high fracture surface energy and the stress relieving ability accompanying when the liquid forms does not exist when it's brittle at low temperatures. So thermal shock damage is usually maximum where the material is still brittle at the lower temperatures. So for the test methods, they demonstrated that properties measured at elevated temperatures should be considered in calculating the thermal shock damage parameters. So again, if you were trying to make a material that's thermal shock resistant by varying the microstructure, the most important property to measure is the work of fracture, in my opinion. Fracture strength is also important. And actually, measuring them as a function of temperature gives you the complete picture of what's happening on these materials. So those were for an MgO material, a magchrome material, and I also had the alumina silica. But this one is for magnesite spinel composites. So the magnesite chrome material has been replaced to some extent with the magnesium spinel materials because there's issues with chrome, um, safety issues with chrome. So this magnesite spinel has replaced some of the magnesite chrome material. So this is thermal shock behavior magnesium spinel composites. It's called a composite because there's a magnesia phase and a spinel phase. And this is a 2004 publication. So they determined the separate effects of spinel particle size and spinel loading on the thermal shock behavior of a magnesia spinel refractory. So MgO is magnesia and the spinel is MgAl2O4. So that's the spinel structure. MgO is cubic, spinel is the spinel structure. So R3 prime, R4 prime were correlated to experimental thermal shock damage. And R4 prime, again, is the work of fracture times the elastic modulus divided by the fracture strength squared, and 1 minus 2 nu, or Poisson's ratio. And the R3 prime does not have the work of fracture term. And again, R3 prime is used to compare materials with similar crack propagation mechanisms. So I don't advise using R3 prime, but if you're measuring similar materials, you could use R3 prime to rank them. So improved thermal shock resistance of magnesium spinel refractories is linked to the large difference in the thermal expansion coefficients. So I mentioned previously that MgO has one of the highest thermal expansion coefficients for refractories, 13.5 times 10 to the minus 6 per degree C. And spinel is about half that, 7.6 times 10 to the minus 6 per degree C. So it's much lower. So in these composites, you have a spinel phase dispersed and an MgO matrix. So there's a thermal expansion mismatch that creates a large tensile hoop stress around the spinel particles. So the MgO matrix is compressing the spinel particles during cooling from the sintering temperature, and it's putting hoop stresses around the spinel particles. And there's a great deal of microcracking. So they're introducing microcracking in this composite to improve the thermal shock resistance. The microcracks are going to decrease the strength. They're going to decrease the elastic modulus. So they're making a lower strength material with a higher work of fracture. So the MgO was high purity, 99% purity. It was a fine particle size material, 0.5 microns in diameter. The spinel, MgAl2O4, is also high purity, 99.5% pure. And they use 3 different sizes to disperse in the MgO matrix: 3 micron, an 11 micron, and a 22 micron particle size. And composites were fabricated from 5 to 30 volume percent spinel powder at these 3 different particle sizes. And they were hot pressed at 1700 degrees C to densify them. So mechanical properties were measured on small bars, 25 by 3 by 3 millimeters. Fracture surface energies were measured on notch bend bars. Strength was a 3-point bend strength. And they got a static Young's modulus off of the load deflection curves from the 3-point bend strength. And they calculated thermal expansion based on a rule of mixtures. You have the 2 end members, and MgO with the high thermal expansion and spinel with the low thermal expansion. You can simply use a rule of mixtures to pretty accurately calculate thermal expansion. Thermal shock was done on the 25 by 3 millimeter bars, and quenching temperatures were from 200 to 1,000 degrees C, and they quenched into a 20-degree C silicon oil, one cycle only, and they measured 3-point bending to monitor the damage, the thermal shock damage. So strength was measured as a function of the spinel content from 0 to 30% spinel. So the circle is the 3-micron diameter spinel. The open, oh, that's the closed circle. The open circle is the 11-micron diameter. And then the solid square is the coarsest spinel addition, 22 microns. So strength decreases with increasing spinel content, and also strength decreases more with the larger particle size spinel. So we're increasing the microcrack density by adding spinel and by making it coarser. Either way, the microcrack density is increasing. You have the same type of effect for the modulus versus the spinel content. The closed circle is the smallest particle size, 3 microns. The open circle is a medium size, 11 microns, and then the solid squares are 22 microns. Exact same trend as for strength. The modulus decreases with higher spinel content, and it also decreases with larger spinel size. And again, either way, higher spinel content or coarser spinel increases the microcrack density. So this is what the microstructure looks like. You can see the gray crystals are MgO. You can almost see some white spots in those crystals are crystallized phase, probably magnesiowustite. And then the light phase is the spinel. So the spinel is dispersed in the coarser MgO crystals, the MgO matrix. And then because of the thermal expansion mismatch, there's a great deal of intergranular microcracking around these particles. So the grain boundaries are microcracked. So they created a microcrack microstructure, and you can plot strength versus modulus, and they both follow the same trend, so should fall along a straight line. This is MgO without any spinel. It should be the strongest. And then the solid circles are shown here. They're up higher in strength and modulus. The open circles are a little bit lower in strength and modulus, and then the solid squares are down towards the bottom here. So strength versus modulus, they're related. And this is the R parameter calculated as a function of spinel content. Again, the solid circles are 3-micron spinel particles. The open circles are 11 microns, and then the squares are 22 microns. So this is a low number, about between 40 and 50 degrees. And this is in Kelvin, so you have to add 273 to that to get degrees C. So it's somewhat above 300 degrees C. And that's where failure should take place under very rapid quench conditions. But because of the high microcrack density, R is not a useful parameter for refractories at all. So the sword elastic strain energy, because of the lower strength, is too low to cause catastrophic failure. So R parameter is generally on a a well-designed refractory for thermal shock resistance are not going to really apply at all. But they did do the calculation, and it doesn't show any trend with the spinel content. So R3 prime was calculated versus the spinel content. So R3 prime increased with increasing loading and size. So the bottom curve is the smallest particle size, 3 microns. The next curve, a little bit higher, is 11 microns, and then the top curve is for the largest size, 22 microns. So going up in particle size, R3 prime increased, and going up in spinel content, R3 prime increased. The work of fracture was also shown, measured and shown here. So work of fracture versus the spinel content. There's a gradual increase in work of fracture with the spinel content. It's not that sensitive at a constant loading to the size, and it's not that sensitive to the particle size. So it does, all three tend to track, all three composites with the 3 different particle sizes tend to follow the same behavior. Loading and size are apparently not that important, but it does, all three increase from about 40 joules per square meter to about 80. And then they calculated R4 prime as a function of the content of spinel. And very similar to R3 prime, R4 prime increased with increasing spinel content and spinel size. Very similar trend as R3 prime. So this is the strength versus quenching temperature, the delta T. So this is pure MgO. It's a strong material. It wasn't designed to resist thermal shock. So you can see when you reach a delta T of about 600, there's an abrupt loss in strength. And then there's some basically a constant strength. The composites are down here. And these are, the solid squares are 20%, 22 microns. The open circles are 30% loading, 22 microns. The open squares are 10% loading, 22 microns. And the triangles are 20% loading, 11 microns. So these are the higher loadings in the larger sizes. They start out with a low strength, and really not a great deal happens. They just continually lose a small amount of strength as you increase the quenching temperature. So this is how you want to design a refractory. You don't want these abrupt changes in strength, which could be catastrophic. You want a gradual strength loss. So if you plot a relative strength versus quench temperature, you can see that these composites have just a steady decrease in strength. These are the best ones, 20% with the coarsest particle, 22 microns, and then the open circles are 30% loading with 22 microns. So the highest loading, the coarsest particles, really maintain their strength as a function of quenching temperature. And then these two curves, lower loading, the triangles are 10% at 22 microns, and then the open squares are 20% at 11 microns. So they show a little bit more strength loss. And then the abrupt loss for the MgO does not contain any spinel phase. So these materials, when they looked at the fracture surfaces, the fracture path was always an intergranular fracture. So it fractured along the grain boundaries due to the microcracking they created. And this one had a transgranular fracture. So it fractured through the grains, through the MgO grains, uh, and eventually went to an intergranular fracture after 600 degrees. So when you have a transgranular fracture, the crack is not being its crack path is not being deviated. You're not creating a very tortuous fracture path. The idea on these materials is that the fracture path is very tortuous. It's consuming a lot of energy, so it has much better thermal shock resistance. Transgranular fracture is really undesirable for that fracture mode is undesirable when you want to make a thermal shock resistant material. So they plotted the fraction retained strength versus R3 prime. This was for quenching at 800 degrees C. Good correlation between R3 prime. The higher the value of R3 prime, the higher the retained strength. And they also did the same plot for R4 prime. It looks very similar. So they can conclude that measuring R3 prime and R4 prime, making those measurements predicted the thermal shock behavior or ranked the materials. So for the microstructure, the separate effects of spinel particle size and then the spinel loading on the composite materials, the magnesia spinel composites. So above a critical temperature, 600 degrees C, MgO, which is not a composite material, exhibited these loss in strength, significant loss in strength. If for the micro crack composites, they all exhibited a gradual loss in strength as the quench temperature increased. They did not have a critical temperature where there's an abrupt change in strength. You do not want that on a thermal shock resistant material. So increasing the spinel particle size, increasing the loading, increase the R3 prime, R4 prime, and thermal shock resistance. And as we previously discussed, the R parameter for crack initiation, the energy needed to start a crack moving, that doesn't really work for predicting thermal shock behavior of refractory materials. And in this particular case for the composites, R3 prime and R4 prime resistance to crack propagation predicted the thermal shock behavior pretty well on these composite materials. So when you're designing a refractory for thermal shock resistance, maybe you're manipulating the microstructure. The simplest thing is just to measure it in the lab, measure it some way, the degradation in a property as a function of some type of quenching experiment. Improving upon that is measuring the properties needed to calculate parameters like R3 prime, R4 prime, or RST, and trying to correlate the microstructure on the fracture surfaces to these parameters and trying to understand exactly what's going on in the microstructure to make further improvements. So the last one I have here for basic refractories is thermal shock resistance of magnesia chrome refractories, experimental and critical evaluation. This is a newer experiment, 2013. So they measured RST and R4 prime. They were correlated to experimental thermal shock damage. And they evaluated 11 commercially available magnesia chrome refractories. And they used two experimental methods to verify thermal shock behavior. So as a function RST and R4 prime were determined both by a static technique and a dynamic method. So they calculated RST and R4 prime, and the E that they used in these calculations, the Young's elastic modulus, they measured two different ways, static and dynamic. And if you recall, the static is going to give you a lower E than the dynamic method because it is under a load. And dependence of bending strength on the delta T. So T max, the maximum quench temperature minus the maximum temperature that you heated the material to minus the quenching temperature 20 degrees C is your delta T. So in these commercially available nichrome refractories, MgO or periclase is the primary phase. There'll be one, two, or multiple silicates, usually a function of the impurity level, but also a function of the lime to silica ratio. And again, the higher the lime to silica ratio, the higher the melting points of these silicates that are present. You usually want a lime to silica ratio greater than 2. And you also have a series of 6 different complex spinel solid solutions. So Mg and Fe2 are the +2 ions. Al, Fe3, and Cr are the +3 ions. And there's a solid solution of all these different spinel materials. The spinel we just looked at in the previous paper was an MgO, Al, oxygen spinel, but in this material, because of the substitution of Fe +2, Al +3, Fe +3, you can have a solid solution of 6 different complex spinels. So these are the compositions of the 11 nichrome materials. So they're roughly 60% MgO, 20% Cr2O3. You have about 10% Fe2O3, 5 or 6% alumina, and 1 or 2% silica. Typical compositions for a magnesia chrome refractory. So they had to add some MgO to the raw chrome or to boost the MgO content up to about 60%. So they measured mechanical properties that sort of randomly, in my opinion, at a series of different temperatures. They measured the work of fracture primarily at 950 degrees C, although they had a few other temperatures also, by a notch beam bend bar on 25 by 25, 150 millimeter bars. They measured the dynamic Young's modulus by a resonance frequency technique on the same size, well, almost the same size bars, 25 by 20 by 150 millimeters. And that was measured from 20 to 1,000 degrees C. They measured the static Young's modulus, and they used the linear portion of the work of fractured load deflection curves, and they got the static elastic modulus at 950 degrees C. They measured the thermal expansion coefficients at 950 and 1400 degrees C. And then they measured the bend strength and 3-point bending on these 25 by 25 by 150 millimeter bars at room temperature, 950 and 1450 degrees C. And I mentioned there were 2 thermal shock modes. The first method, they used a cylinder, 50 millimeter high cylinder by 50 millimeters in diameter. So this is a typical size. It's basically a 2-inch diameter, 2-inch high cylinder. You can also use a 50 millimeter cube. So the quenching temperature range, well, it was from 950 to 20 degrees C. So that's quenching from 950 to room temperature water. And they keep quenching these cylinders until they reach a 20% volume loss. So the number of cycles was variable until 20% weight loss was reached. This is one way to do a thermal shock test. It's more qualitative, it's not quantitative. The second method is more quantitative because you could put a number on it through a bend strength. So this is the 25 by 25 by 150 millimeter bars. And the quenching temperatures range from 400 all the way up to 1200, 600, 700, 800, 900, 1000, 1100, and finally 1200, quenched in an ambient air. So they did 5 cycles in ambient air, and then they measured the 3-point bend strength. So these are 2 typical ways thermal shock damage is measured: simply cycling a cylinder or a cube until it falls apart. So the more cycles, the better it is. The more cycles it survives, and then the quenching and getting a number, whether it's a 3-point bend strength number or a decrease in modulus or a decrease in sonic velocity, it's quantitative. So when they measured the fracture surface energy using these notch bend bars, they get a load displacement curve that looks like this. It's stable. The area under the curve is the energy that goes into the work of fracture calculation. But they stopped the test at 15% of the maximum load. And they said they were avoiding compressive forces in the upper surface, upper part of the bend bar sample. I usually like to run these all the way out. The displacement is usually pretty large, and the crack mouth opening displacement is pretty large. So I'm not sure how much compressive stress is actually in the upper portion of the sample because of a large amount of crack opening, but they did stop them at 15%. So here are the 11 refractories, and they measured a series of other properties. They measured the open porosity, usually around 12 to 15%, the apparent density, grams per cubic centimeter. They're all around 3.1, 3.2. The compressive strength in megapascals. These are maybe from 20, low of 27 to high of maybe 64. So there's a factor of 2 difference. They also measured the gas permeability. So there was open porosity. Was that porosity connected? So some of them had a higher permeability. This is 9.7, 8.4, and then somewhere about half, around 4, and somewhere even about a quarter. So some of these refractories had more connectivity on the porosity. Then TRS is the thermal shock resistance test with the cylinders. So they were held at 950 degrees C for 25 minutes, dropped into water for 3 minutes, dried, and that cycle was repeated until you got a 20% weight loss. So the best refractories were maybe 14 or 13 cycles, and the worst ones were maybe 7 cycles. So about a factor of 2 difference in the performance. The bending strength in megapascals was measured at room temperature 950 and 1450 degrees C. And you can see the strength is falling off at the highest temperature because of the amount of silicate phases, low viscosity silicate phases at that temperature. The work of fracture in joules per meter squared was measured at 950 degrees C. Some are low, around 77. Some are about 3 times higher, 211. And then the expansion, average coefficient of expansion at 950, room temperature to 950 and room temperature to 1400 degrees C was measured. You don't have, you can't really manipulate this. It is what it is. They're all about 10 uh, times 10 to the minus 6 per degree C. So you're stuck with the elastic, with the thermal expansion coefficient. So this is the dynamic modulus as a function of temperature. So E as a function of temperature, there's a heating curve and then a cooling curve. They measured it on heating and cooling by resonance technique. And they don't give a great explanation on some of this, but there's an increase in E above 600 degrees C. And I think that's primarily because microcracks are closing. The spinel structure also has an inversion in that temperature range. So there's a normal spinel and an inverted spinel. So I probably, because of microcracks closing, the modulus goes up. And then they don't really explain this kind of behavior, but probably I would guess the silicate, the viscous, or it's pretty fluid, then it becomes more viscous. The silicate phase, the glassy phase, probably solidifies. There's probably a lot of rearrangement of that distribution. It solidifies, giving you a higher elastic modulus here, and then the microcracks open again upon cooling and the modulus decreases. That's the best explanation I can give for this behavior. Again, this was for material 1. This is for material 4. Same type of behavior, probably closing of microcracks, giving rise to an increase in modulus, probably a solidification of the glassy phase and then opening of the microcracks. So E is definitely not constant with temperature. So again, it begs the question, which modulus value do you use in that, from what temperature, in calculating the R parameters? This is material 7. Again, probably microcracks closing, and then maybe there's not much silicate phase present. Then you have your microcracks opening upon cooling. And another material, 10. This is more typical of modulus decreasing with temperature, maybe the microcracks closing and increase, followed by a decrease with the microcracks opening. And then one more material, 11, a decrease in modulus, I would say, is typical behavior, closing of microcracks, and then this decrease to the opening of microcracks. So these 3 materials make a lot of sense to me. These maximum humps in this curve, I gotta believe, are due to stiffening of the silicate, a great deal of silicate second phase. So I sent you the papers. For some reason, the subscripts didn't come out too good here. This is E sub D. So this is the dynamic modulus measurement at room temperature at 20 degrees C. This is the static E sub S at 950 degrees C. And then this is the dynamic at 950 degrees C. H is for heating. These are the ones, the 5 graphs I just showed you. They only measured 5 materials. And this is E dynamic cooling at 950 degrees C. What you can compare here is static versus dynamic, whether it's heating or cooling. You can see the static modulus is quite a bit less in any of these cases than the dynamic modulus. And that's just to be expected. So this is 1 through 11, all 11 materials. And then these are the materials I just showed, 1, 4, 7, 10, and 11. that had the dynamic modulus measurements. So for Young's modulus, the first line here, all 11 materials, this is a static dynamic. This is the static modulus at 950 degrees C. And then these other ones, this is dynamic heating, dynamic cooling, and then this one is static at 950 degrees C for these five. So they look at two correlations here, one for RST and one for R4 prime. So this is R sub ST, this is R sub 4 for R4 prime. And they use the cylinder thermal shock resistant test, TSR. So this is for the cylinders where they took the number of cycles at 20% weight loss. So this is the thermal shock resistance equals some function of RST. The thermal shock resistance equals some function of R4 prime. So for these four cases, they use these different elastic modulus values, and they're quite different. They wrote an equation, TSR equals 0.5814 times RST plus another constant, 5.1753. So they developed equation in terms of RST for each one of these, and they got a high correlation coefficient. So they're saying, well, a high correlation coefficient, RST is a good predictor of the thermal shock behavior. But when they wrote these equations for R4 prime, the correlation coefficients were really low, so they did not develop any equations for R4 prime, and they concluded that R4 prime was not correlating with the thermal shock behavior. So these are relatively weak materials. They're probably, when we look at that delta T versus crack length plot, they're probably to the right of the minimum where this RST applies for that quasi-static crack growth. So the thermal shock resistance versus RST. And this first one is E dynamic at 950 cooling. This is E dynamic at 950 heating. And then this is E static at 950. So three different ways of calculating the elastic modulus. Each one gave a pretty good correlation. If you do a regression analysis, you get straight line curves. So no matter which version of the elastic modulus you used, they seem to correlate with this thermal shock test, the cylinder type test, quench test with RST. And then this one is for the static modulus at 950 for all 11 materials. So the thermal shock resistance plotted against RST for all 11 materials with the static elastic modulus they measured at 950 C. And again, they get pretty good correlation. The higher the RST value, the more cycles that withstood before 20% damage. So for most materials, they measure the work of fracture at 950 degrees C. But for these three, 1, 5, and 11, they measured it as a function of temperature, 450, 700, 950, and 1200 degrees C. And you can see what's happening in any of these materials. As you increase the temperature, the work of fracture goes up, and it's substantial. This is 66 here. It's 204, roughly 4 times higher, 45 here, 193 again, roughly 4 times higher, about 100 here, about 400 here. So usually about a 4-fold increase on these materials. And that's because of the formation of the viscous silicate glasses in this temperature range. It actually starts forming at lower temperatures, more like 950 in some of these materials. So work of fracture is increasing as a function of temperature. And then they measured the strength as a function of delta T, the quench, and this is for the bars after 5 thermal shock cycles. And they're showing 1, 4, and 11 materials here. And you can see some of these materials like 11 performed pretty well, and then 1 and 4 started to fall off in the strength as the delta T got higher. They didn't do a lot of correlation of R4 prime or RST with this second thermal shock test. But what they concluded is the R4 prime parameter for this unstable crack propagation. And that's where we have some excess kinetic energy. We're to the left of the delta T versus crack length diagram. And they're saying R4 prime didn't really predict the thermal shock behavior of these 11 mag chrome materials. But they said RST, where we have stable crack propagation, the quasi-static mode, predict the thermal shock behavior of these 11 chrome materials. So this paper had quite a lot going for it, all different kinds of measurements at all different temperatures. And the final conclusion is RST predicts the thermal shock behavior, whether it's a cylinder quench or a bar quench. So that's what they concluded. So that's 4 different case studies on basic refractories. And next class is zirconia. Zirconia is more complex because it has a phase transformation just like silica. So we'll do the zirconia materials next class. And then the second lecture next week will be on non-oxide materials like silicon carbide, silicon nitride. And then finally, we'll spend most of the time, at least the solid week, 2 lectures on the magnesite carbon composites, the aluminate carbon composites, all the carbon matrix composites, which really show good correlation with these fracture parameters, these R parameters. So have a good rest of your day. Have a good weekend. And thanks for listening today. See you next week.